Hi there. Today we're going to be talking about voltaic, also known as galvanic cells. So another application of electrochemistry that is pretty important. So what is a voltaic or galvanic cell? A galvanic cell or voltaic cell, named after scientists Luigi Galvani and Alessandro Volta respectively, is an electrochemical cell in which the electric current is generated from spontaneous redox reactions. So the idea is that it's spontaneous. The voltage is happening above zero for these. A common apparatus generally consists of two different metals, each immersed in separate beakers containing their respective metal ions in solution that are connected by a salt bridge or separated by a porous membrane. So what does all this mean? Well, let's take a look. For this example, what we're going to be doing is looking at a cell made with copper and chromium, and again, their respective ions. So you'll notice I have copper in this is copper metal, sitting in a solution that contains copper 2+. I have chromium 3+ ions and a chromium metal placed in that solution. So I can figure out what their potentials are by going back here, looking at the potentials for oxidation and reduction. And what I notice is, so my chromium is here, my copper is here. One of these has to be reversed to make this a spontaneous reaction. So we find the more negative of the two, and we're going to reverse that reaction. So the chromium is actually going to undergo an oxidation at a voltage of positive 0.74 volts. Then we'll have the reduction of the copper ions at a positive 0.34 volts. So it looks like we have a positive 1.10 volts for this particular reaction. Now again, the chromium is undergoing the oxidation, the copper 2 is undergoing the reduction. We know that because we flipped the more negative value so that the sum of the two voltages is positive. Thus, it is a spontaneous reaction. Now that I know which side will contain the oxidation half reaction and which side contains the reduction half reaction, and I've indicated that here, I can figure out direction of electron flow. So the chromium is undergoing the oxidation, we decided. That means it's losing electrons. The copper 2 in the solution here is going to be gaining the 2 electrons. So the electrons are going to travel in this direction, provided that I allow them some sort of means to do that. So a wire, obviously, it would be the easiest choice. So the electrons are going to be moving in this particular direction. So we have some names for these electrodes at this point. The one that's undergoing oxidation is always called the anode. So the chromium is acting as my anode. And that, again, is where the oxidation is occurring. Over here, where the electrons are heading to, is my cathode. And that is the site of the reduction. I kind of remember that because the anode and oxidation start with vowels, cathode and reduction start with consonants. So, electrons move from anode to cathode. By the way, if this were assigned a certain sign, that would be negative and this would be positive. I'll explain that later. All right, so now we have a means to move the electrons from place to place at a positive potential of 1.10 volts, but nature won't allow charge to build up in one side. I can't simply move electrons to this side. That would create a positive charge over here and a negative charge over here. Nature doesn't like that. What we need to do here is create a salt bridge that's going to allow ions to migrate from one side to the other to keep things electrically neutral. So a salt bridge is always just some salt that's not participating in the reaction. Sodium chloride would work, potassium fluoride, about anything, any soluble ionic salt. I'm just going to call it X plus and Y minus. Okay, so I have some ions that are positive, like sodiums. I have some ions that are negative, like chlorides, and these are going to be connecting these two beakers together. All right, well, imagine maybe it's a tube full of these ions. That'll make sense. All right, now, because the electrons are moving into the cathode side, whatever positive ion there is in my salt bridge has to move in that direction as well, because if this is building up a negative charge, the X's will come in to neutralize the charge. The right side, the anode side, is losing negative charge. The electrons are moving to the other cell. So the anions are going to move into that solution to compensate for that loss of charge. So now we have a cell that will be working. So what's going to be happening over time with this thing? We're obviously losing mass at the anode. The chromiums are becoming chromium 3+. It's important to understand that this thing is actually getting smaller. Over here, the copper 2+ is plating itself onto the copper electrode. So the cathode is actually gaining mass. The solutions, the copper 2+ solution is becoming less and less concentrated. The chromium 3+ is becoming more and more concentrated as this reaction proceeds. Okay? You may ask, how does a battery, which obviously we're looking at what is called an electrochemical cell component of a battery. Batteries die because you run out of anode or the ions around your cathode. Sometimes your salt bridge gets a little corrupted too. But we'll talk about some of those things. So that is the basic workings of a voltaic cell. The anode is losing electrons. The atoms are jumping off into the solution in their oxidation reaction. The cathode is gaining the electrons. Therefore, the ions that are in that solution are being reduced onto the electrode, making it gain mass. The positive ions in the salt bridge are going to flow towards the cathode. The negative ions in the salt bridge are going to move towards the anode. And this thing should be running at a voltage of 1.10 volts because we looked at our reduction table and figured out what those voltages were for each half reaction and added them together. Over time, of course, the voltage will start to drop as your anode loses mass and as your cathode solution becomes less concentrated, but that is a discussion for another class. So thank you very much.